Yeah. Okay. So I think this idea is clear. So we convert point-to-set mapping to point-to-point mapping, and using Brouwer's, I get a sequence of fixed point. I apply Bolzano-Weierstrass to the sequence. I get a convergence subsequence that converges to some points x naught within S. Now my claim is that x naught is my desired point. Okay, so how do you prove this? The proof is not very difficult. So suppose your fixed point, I mean, you lie in a particular subdivision. So let's call it say delta n, and suppose the vertices of the delta n are denoted by this x naught n, x1 n, and xr. So you can express each of xn. You can express each of xn by a convex linear combination of your vertex. I mean, vertex of the particular simplex that it belongs to. I mean, subsimplex we call it. You should call it. So this is your representation. And if there is a subsequence of xn which converges to x naught, then you can easily see that you can look at the corresponding subsequence of vertices. You can look at, if you look at the corresponding sequence of vertices, that also converges to x naught, isn't it? Because as your division is getting finer and finer, the vertex of the subsimplex and the corresponding point, if you look at these two, the distance between this fixed point and the vertices of the simplex is at most bounded by a very small number, because this subdivision is getting smaller and smaller. So after some large n, I mean, diameter of each subsimplex will be very small. So if this sequence of points xn gets converges to some point x naught, then the corresponding sequence of vertices that will also be converge to the same point x naught. Yeah. So yeah, that's right. And then this is just some easy calculation, which is that so this xn are your fixed points. So xn is just phi n of xn, and since your xn is sum over this thing, and I've extended the map linearly. Remember that I only have the point-to-point map from the vertices of the subsimplex to some points in the simplex, and I have extended the map linearly to the whole simplex. So if xn is summation lambda I n xin, then my phi n of xn will be summation lambda I yn. I mean, where this yin is exactly equal to my phi n of xn. So that is the thing. And then what you can do is you can take a further subsequence of this lambda i's. So remember that all of my lambda i's actually belong to closed interval 0, 1. All of them are positive, non-negative, and all of them belongs to 0, 1. So I can also find a subsequence of this lambda i's which converges to say some lambda naught. Yeah. So yeah. So from this lambda in, you can find a subsequence which converges to lambda I naught, and from this yin we can also find a subsequence which converges to yi naught. Okay. Right. So from there, what you get, your x naught is nothing but summation lambda I naught yi naught, because your xn is converging to x naught, I mean a particular subsequence, and you are reducing to a further subsequence where your lambda i's are converging. Similarly for yi's. So by the properties of basic properties of limit, x naught will also be equal to summation lambda I naught to y naught y n, and then use the upper semi-continuity of the function. So by upper semi-continuity, what you know? By upper semi-continuity, you know that, yeah. So this YINC belonging to this phi of XIN, right? And this XINs are converging to the point x naught, and your YIN, a particular subsequence of that, is converging to YI naught. So by upper semi-continuity, what you have? You also have, let me clear this. Yeah. So by upper semi-continuity, YI naught also belongs to phi of x naught. This is just by upper semi-continuity of the function. This yi naught also will belong to phi of x naught. And now, because your phi of x naught is a convex set, so this linear combination will also belong to phi of x naught. So your x naught also belongs to phi of x naught. The proof is done. So that is your fixed point. Yeah. So idea is simple. I will just sum up the whole idea. So you have a simplex. Then you create simplicial subdivisions. So as your division gets finer and finer, the vertices of a particular subsimplex and the fixed point and the subsimplex where the fixed point lies. I mean, distance between the vertices of that subsimplex and the fixed point is very small after some large state. So yeah, then you reduce everything to a subsequence by Bolzano stress, and from there you are getting the desired point. Yeah. So this is the idea. So this is the idea actually. I mean, this is the original proof. I mean, the Kakutani gave in his original paper. So yeah. So Brouwer fixed point theorem we had, and then as an application we showed this Kakutani's fixed point theorem. Yeah, and in particular, I mean instead of a simplex, you can take any closed convex set. I mean that will also work. That will also work. Topologically, I mean these two things are not really different. So the same argument will work up to some modification. Okay. So in particular, you take something like circle or anything, the idea will also work. Okay. Okay. Now I will discuss some applications in game theory. Yeah. So yeah, this is another version of Kakutani's fixed point theorem. I mean, you can call it a application of fixed point theorem. So you look at K and L, two bounded closed convex subset in your Euclidean space, say Rm and Rn. You're looking at two bounded closed convex subset, and then you look at the Cartesian product K cross L in Rm m plus n, and you take two closed subsets U and V of K and L of K cross L. Take two closed subset U and V of K cross L, and then for any x naught belongs to K, you look at all possible y in L such that x naught comma y belongs to U. Okay, it's better to draw a picture. Yeah, yeah. So for simplicity, let's take m is equal to n equal to 1. So you have a closed set. You have a closed set here. Let's say K, and you have a closed set here. Let's say L. So this is your K cross L. This is your K cross L. Now you take two closed subset of this rectangle. Suppose you take some U here and some V here, and you look at a particular point x naught here, and then you are looking at all y. You are looking at all y such that x naught comma y belongs to U. So you are looking at a portion like this. Yeah, you are looking at a portion like this. So you're looking at all y such that this x naught comma y belongs to U. Okay, and similarly for a fixed y naught here, you are looking at all possible x such that your x y naught belongs to V. Yeah. So this will be a portion like this. Yeah. So this is the set of all possible x such that your x comma y naught will belong to V. And suppose you are given that for every x naught, for every x naught and for every y naught, these sets are closed and convex. So for a fixed x naught, I am looking at all possible y such that this x naught comma y belongs to U. So the set of all possible u's like this, set of all possible y's like this is a closed set. Suppose is a closed set, and similarly for this thing, it's a closed set. So under this assumption, what will happen? Your U and V will have a common point. So this intersection will be non-empty basically. Yeah. So that is what we want to prove. So that is what I've written. I mean, for a fixed x naught, look at all y such that x naught y belongs to U. That is your U x naught. And suppose that is non-empty, closed, convex. And for a fixed y naught, you look at all possible x such that x comma y naught belongs to V. That set is also closed and convex, and under this assumption, even we have a common point. So I'm not going through the proof completely. Yeah, you can just do it yourself. I will just give the sketch, which is that so you just define a map from S to RS by, I mean, the natural map that you can think of. You map a point x comma y to the subset Vy cross Ux. Yeah, so remember what is Vy? Vy is set of all x in K such that x comma y belongs to V. And what is Ux? The set of all y such that x comma y belongs to U. So you map this x comma y to the subset Vy cross Ux. So you get a point to set mapping. And using the closeness of the set U and V, you can easily see that you can easily verify that this map is upper semi-continuous. Then apply Kakutani's fixed point theorem. You have a fixed point. So there is a x naught comma y naught, which belongs to Vy naught cross Ux naught. From there, it is just a tautology that x naught comma y naught belongs to U intersection. So this is just a very easy application of Kakutani's fixed point theorem, and some people call it some Kakutani's fixed point theorem is another version. Yeah. I mean, I don't know Kakutani proved this himself or not, but some people call it fixed point theorem too. Yeah. So so I mean those are the theorems I wanted to discuss. I mean there is one more important theorem in game theory, which is called minimax theorem. Obviously, I will not go through the proof. So just look at the statement. So if you have a continuous real valued function defined on k cross L, where k and L are again some bounded closed convex sets in Rm and Rn, and then for a fixed x naught, you look at all possible y such that f of x naught comma y bounded by some positive number alpha is convex, and then again you fix a real number beta such that set of all x belongs to k such that f of x comma y naught is greater than or equal to b. This is also convex. So this is a condition of the theorem. So depending on if you are creating two convex sets, actually you're fixing a x naught, looking at all possible y such that f of x naught comma y has an upper bound by a fixed real number which is convex, and similarly for a fixed y naught you are looking at all possible x such that f of x comma y naught has a lower bound by a pre-given fixed real number that is also convex. And under this assumption you can prove that you can switch the max and min. If you take the maximum, if you take the minimum over L, then maximum over k, and if you reverse the order, I mean both are same actually. So max min equal to min max. So this kind of theorems are very important in doing in doing the theory of zero sum games. There is a thing called zero sum game in game theory. So I will not go into the details. So right. So roughly, I mean these are all the theorems. So yeah. So I hope the ideas are clear. So anyone have any sort of question or comments up to now? So your basic ideas are clear, I guess. But
yeah, quite nice.
yeah.
Do you want to discuss the Nash equilibrium a bit, or?
Yeah, I will just briefly give a sketch. I mean, how it can be related. So,
Okay. Yeah.
I will probably
Go
take
ahead.
10 more minutes or something like that. So, so Nash equilibrium is a very famous thing in game theory. This earned John Nash the Nobel Prize in Economics. So this is a very celebrated thing in game theory or economics, whatever you call. So what we have is that if you have this simplex, okay, let me draw. Yeah, so you have this simplex. So suppose so like Agrup was discussing some game, like and in a game you have a strategy. So suppose there is a player, let's call it P naught, and he has some strategies. Okay, he has some base level strategies. I mean, which can be represented on the vertex. So suppose this player has three strategies, which are represented by the vertex of this triangle, and then it is also possible for the player to take a combination of these strategies. So this is you can think of it like some probabilistic thing. Suppose the player chooses x naught with probability lambda naught. He chooses x1 with probability lambda 1. He chooses x2 with probability lambda 2. And you know that the sum of the probabilities add up to 1. So, I mean, each of his possible strategies can be represented by a point in the simplex, precisely by the point lambda I xi. So that is how you represent your space of all strategies by every point in the simplex. So that is the correspondence. Yeah, so that is the correspondence. So these are your base level strategies, and from there a player can take any possible combinations of these strategies, which is represented by an interior point of the simplex. Right. That is what I've written here. I mean, define a define a set S to be the set of all tuples of mixed strategies chosen by each player in a game. And if each player has k possible actions, then each player strategy is a k tuple of probabilities summing up to one. The thing I said. So each player strategy space is the standard simplex Rk. And suppose you have n players, so you can view this space of all strategies in Rkn. So that's the thing. And then what you do is that this function, somehow you create a function phi which associates, I mean, each tuple, a new tuple where each player's strategy is her best response to other players' strategies in X. Okay, so somehow depending on the point, so remember in Kakutani's fixed point theorem, we have a point to set map. So and is X is representing a particular strategy of other players. So depending on the other player's strategy, somehow this phi X is denoting the strategy of the next player. So that is what that is the way you can think of this map phi. So and since there may be there may be a number of responses which are equally good. Okay, so in decision making, what happens? I mean, depending on a decision, it is possible that there are multiple choices, there are multiple decisions which are equally good for you. You can take. So corresponding to each decision, you do not have a single decision. Rather, you have a spectrum of decisions. You have a set of decisions. So this map is really a set value map. Every point is getting to a possibility of good strategies. So this phi x is a set valued map rather than single valued, and for each x, this phi x is non-empty since there is always at least one best response. And this set will be convex because a mixture of two best responses is still a best response. So I mean, I'm not going into the details. I mean, this comes from the rigorous formulation of game theory. You can rigorously define what you mean by a best response and things like that. And from that, you can prove that this phi has a closed graph. So I mean, by closed graph, I mean that just upper semi-continuity property. And then by Nash equilibrium, what we mean is that this Nash equilibrium exactly correspond to a fixed point of your map phi, which is ensured by Kakutani's fixed point theorem. So this just means that a tuple of strategies where each player's strategy is a best response to the strategies to the other players. So if you have to find a tuple of strategy such that each player's strategy is a best response to the strategies of the other players. So I mean, this is known as a Nash equilibrium for the game, and the existence of equilibrium is is guaranteed by this Kakutani's fixed point theorem. So yeah, so I hope I mean you are getting some idea, right? Yeah. So anyone have any comments? I mean. Yeah, sorry, I think you were breaking. Yeah, okay.
Yeah, sorry. No, it's all fine. So of course the game theory part requires more details. And can you give the reference from where you read about Nash equilibrium?
Yeah. So actually, I will end with a small anecdote. So from there, actually, we'll find a reference. Okay. So yeah. So I will just end it. I mean, yeah. So maybe yeah. So there is a game theorist called Ken Binmore actually. So there is a small anecdote that Ken Binmore recalls that in a conference, Kakutani was asking him that why uh, there are so economists who are attending his talk, and then Binmore said that it was probably because of the Kakutani fixed point theorem. And then Kakutani replied that, I mean, what is the Kakutani's fixed point theorem? So it seems like he did not give the name fixed point theorem himself. I mean, other economists actually find this theorem very useful and they labeled it by a name actually. So Kakutani himself did not realize that how useful it will be in the areas of uh, decision making, game theory, and this economics and all. I mean, many fixed point theorems is very useful outside mathematics actually. All of this kind of fixed point theorems. Always fixed point theorem shows up uh, in some strategy problem actually. So yeah, so you can actually look at the book of Ken Binmore. I think this also have good historical references and all. So
Hey, Sushant saying he
yeah. I will just
couldn't
check in
unmute
the
himself.
chat.
Theorem, but then later on he was able to simplify the proof and use only the Brouwer fixed point theorem. I don't remember exactly the details, but so there was a simplification of a proof either by himself or someone else. I don't remember, but there is a possibility to prove the Nash equilibrium theorem just by using the Brouwer fixed point.
Yeah, so you were saying there is a proof without using Brouwer, right?
Without using Kakutani.
Kakutani, okay, without using Kakutani.
Yeah, just a simple Brouwer fixed point theorem. I think Nash himself proved it using after a couple of years of his the original publication used Kakutani's fixed point theorem, but after a couple of years he kind of realized that okay, he can simplify the proof and use only Brouwer's fixed point theorem.
Yeah.
Okay.
Okay, I think
maybe
Sushant, you can unmute now, I think. Can you unmute now? I don't know what's happening because Sir can speak, right? So you should also be able to.
Yeah, I also can speak.
Yeah, I have clicked on the security and I have allowed the participants to unmute themselves. So there should be no problem, right?
maybe you can write the question in the chat box. Is that possible?
Because others are able to speak, so I think maybe you should leave and join again. Yeah, so you are saying
N equal to 2.
is this the simplest proof of the Brouwer's fixed point theorem? Okay, so for n equal to 2, yeah, I mean, after you know your basic knowledge of fundamental groups, I mean, this is the easiest proof, right? Or what do you think? Or anyone else think something else?
There are other proofs, but then you would have to assume some other stuff, like for
Right.
example, if you have a quantitative mapping or something.
Right. Actually, there is some proof which are like this. I mean, So you approximate your continuous map by a differentiable map. So since you are in Rn, so you have a differentiable structure. So you approximate a continuous map by a differentiable map, and then use some tools from differential topology. So for example, there is a thing called degree of a map. So I think historically the first proof actually Brouwer gave, that is based on degree theory. So degree basically means, I mean, you look at a particular point and then look at the pre-image of that point. So you have a map from here to here. Say you have a point here, and then you look at all the pre-images of this point. You look at all the pre-images of this point, and you look at the Jacobian of the map at this point, at these points, and look at the sign of the Jacobian. So basically, the sign of the determinant of the Jacobian, and then you sum all these signs up. Yeah, you sum these signs of date of Jacobian at a point y, where y belongs to if inverse if. So this is known as the degree of a mapping, and then you can show that under homotopy, if and g are two homotopic map, then degree is also invariant, and from there you can show actually, and yeah, there is a whole literature on degree theory. Using this degree theory, you can prove many theorems in one shot. I mean, for example, many things we did through these presentations. For example, Bose-Equilam theorem, Jordan curve theorem, many fixed point theorems. All theorems you can prove in one shot by using some degree theory. There is a whole literature on degree theory, actually. So this one thing I know. That is another
Very nice.
way to prove. You approximate your continuous map by differentiable mapping by standard Weierstrass approximation. There is some Weierstrass approximation in general spaces. So that is the idea of a degree. Also, there are some proof which uses the idea of Stokes. So you are having a retraction from the whole set to the boundary of the set, and then you define some differential form, and then you integrate that differential form over the boundary. Then you can apply Stokes theorem, and then somehow you can get a contradiction. So there are various ideas, but I think this proof, yeah, this once you know the nth idea of nth homotopy group, so this homotopy proof is really very straightforward and understandable. So yeah.
I also
Yeah, sorry, I think you're breaking.
you know. Hello.
Yeah, I can hear you.
Yeah. I'm asking that, do you know of any proof of Kakutani's fixed-point theorem which uses the Hausdorff metric on the space of closed convex subsets?
Yeah, we
I
had
mean,
this
you can
problem.
use-
Yeah.
Right. The proof that I saw is the same that you presented here. But I haven't seen any proof that uses the Hausdorff metric, but it seems like it should be something that one can apply.
Ah, I see. Okay, yeah, that is interesting. Yeah.
Okay.
So yeah, I think that is all I had to say, and yeah, so thanks for listening. And I think, yeah, this is the last presentation, so we are ending the course here, I think.
Right. So I hope you guys enjoyed the course. I enjoyed teaching you guys very much, and I hope you got to learn some new things at least.
Yeah. So
And,
when
best of luck.
So
Yeah.
when are you coming to the campus?
Oh yeah, that's $1 million question. I don't know. I mean, the way it was spreading, I got really just not ready to take the risk. So hopefully by March I'll get the second shot for my vaccine, and then I can come.
Okay, I see.
Yeah, yeah. Sorry about having the whole course online, but it was just
No,
a
it was
pity.
fine here.
Yeah. Okay, so best of luck for your next semester, and since we're not having the exam, if you have any questions with the assignments, just let me know. As I said, we can discuss about it. I mean, this is how research is done, by discussing with people. So
Yeah, yeah.
it's completely fine to discuss, but just make sure you understand. If you discuss and find a solution together, make sure you understand the solution and write your own answer when you're submitting the assignment. So that's all I want. Okay. Okay. Good luck. So we end the call here.
Okay, thanks to everyone, and we'll just end the meeting if no one has anything to
Yeah.
say.
Yeah. Bye, guys. Hope
Yeah,
to see you
bye.
around.
Bye, sir.
Yeah. Bye.